Hi everyone, I am Amir Iqbal from the Trace Lab at the University of Massachusetts Lowell. In this presentation, I will talk about our research on provably stabilizing controllers for quadrupedal robot locomotion on dynamic rigid platforms. This work is done with my labmate Yuan Gao and my advisor Dr. Yan Gu. Our paper number is 0179. Quadrupedal robots have great potential in negotiating complex environments during critical real-world applications such as transportation and disaster relief. Many of the locomotion platforms involved in these applications have rigid surfaces and exhibit significant movement in the inertial frame. We call these platforms as dynamic rigid platforms. Real-world examples of these platforms include an industrial floor, floating bridge, hanging bridge, floating vessel, a disaster site, cruising aircraft, etc. In this study, our goal is to derive a control framework that enables quadrupedal robot walking on dynamic rigid platforms. Control of legged robots is difficult and still an evolving research area. Since the introduction of ZMP approach in 1972, the controller for static terrain locomotion is extensively researched. Recently, the controller for locomotion on deformable terrain and rigid moving terrains are investigated by many researchers. Some of the notable works are shown here. When moving on a dynamic platform, the robot motion is also affected by platform movement at the contact points. To date, a controller design that explicitly addresses the platform movement remains missing. The challenges for controller design of elect robots stem from multi-domain, nonlinear hybrid dynamics with state-triggered jumps. For dynamic rigid platforms, this complexity is further increased by presence of time-varying holonomic constraint at the robot platform contact points caused by platform movement. The holonomic constraint for a static platform is time invariant. Our research objective is to derive a control framework that explicitly addresses platform movement for realizing quadrupedal robot walking on dynamic rigid platforms. For attaining this objective, we first develop dynamic model of the system, then generate optimization-based feasible trajectories. Finally, design a tracking controller based on formal closed-loop stability analysis. The derivation of dynamic model of the system is presented here. Method of Lagrange is used for modeling the nonlinear hybrid time-varying robot platform dynamics with state-triggered jumps. At any instant, three of the four legs of the robot are in contact with the ground, which makes the robot fully actuated. In this study, we considered a dynamic rigid platform with known movements. This type of platform is chosen because many of the real-world platform dynamics may not be known. However, the motion of the rigid contacting surfaces may be estimated or sensed. A faithful model of the robot dynamics is critical to the reliability of control design. Robot walking is naturally a hybrid process. During a continuous phase, the robot has one leg moving in the air. The dynamics are described by second-order ordinary differential equations. When the swing foot lands on the platform surface, an impact occurs. This landing event can be described by a switching surface. The impact dynamics are modeled as discrete reset map. The map explicitly depends on the platform motion. From this equation, we can clearly see that the robot dynamics are hybrid, multi-domain, time-varying, nonlinear with state-triggered jumps. These state-triggered jumps cannot be directly controlled because it is of infinitesimally short duration, which adds to the complexity of controller design and stability analysis. Furthermore, the explicit time-varying nature of continuous phase and impact dynamics further complicates the problem. The time-varying holonomic constraints, when incorporated in equation of motion, the reduced order model for the system is obtained. The holonomic constraints, contact force, and impact map expressions explicitly depend on the platform motion and thus are explicitly time-varying. Planning and control of a walking robot are based on this model, so they are aware of the motion of the platform. Since the planning is not focus of this research, I will skip it here. Details can be found in the paper. Controller design for the system is presented here. In this study, Stable walking is enabled by trajectory tracking control. If the reference trajectories are feasible and the robot can reliably track them, then stable walking is automatically guaranteed. The variable of interest for control are chosen as robot's base pose and swing foot position. We choose to control the base pose to maintain a relatively steady pose of the robot while walking. Also, the swing foot pose is chosen to avoid bumping the swing leg in any obstacles or surface during walking motion and reach the desired landing location. The tracking error is defined as deviation of control variables from the reference trajectories. The closed-loop dynamics of the system have explicit time dependence due to platform motion. Both the impact map and continuous phase dynamics have explicit time dependence. Since the discrete phase is instantaneous and thus cannot be directly controlled, hence only continuous phases are utilized for control. To simplify the controller design for the non-linear robot platform system, input-output linearization is used for linearizing the system. We design a PD controller for the linearized model. If we properly choose the PD gains, the controller will ensure exponential convergence to the reference trajectories during a continuous phase. However, the discrete impacts will remain uncontrolled. To deal with the uncontrolled jumps, we have established sufficient conditions that the continuous phase controller should satisfy such that the closed-loop hybrid system is stable. To derive the closed-loop stability conditions, we have performed the stability analysis of the closed-loop hybrid system based on the construction of multiple Lyapunov functions. A hybrid system is stable if it meets these two conditions. These conditions are also illustrated in the graph. During a continuous phase, the Lyapunov function's candidate exponentially decreases, and the sequence formed by the values of Lyapunov functions right after each impact is strictly decreasing. I will skip our complete stability analysis. Instead, I will briefly explain one key step in our stability analysis, which is the analysis of tracking error evolution across the impact map based on the triangle inequality. The analysis shows that the norm of the state right after jump is bounded above by a function that is proportional to the norm right before the jump. Details of stability analysis are given in the paper. The analysis produced sufficient conditions that can guide the tuning of PD gains for ensuring closed-loop stability. To validate the derived model and proposed controller, we have performed simulations in MATLAB and PyBullet and hardware experiments. The validation cases and simulation and experimental setups are presented here. In MATLAB, we simulated the robot walking based on dynamic model we just introduced. We incorporated joint torque saturation of the real robot. In PyBullet, we built a dynamic platform to emulate geometric and physical properties of the actual platform that we used in experiments. In experiments, the dynamic platform is a split bell motor treadmill with pitching motion. The treadmill is available at Huma's Lowell Nerve Center. We conducted a comparative PyBullet simulation to demonstrate that a controller that does not explicitly consider the platform motion may not ensure stable walking. We first design a controller that works well for static terrain, as the video on the left shows. However, this controller cannot guarantee stable walking when the robot walks on the pitching treadmill, as the video on the right shows. This slide shows the simulation and experimental results videos for two of the five validation test cases. The first row shows MATLAB, PyBullet, and experimental results for the case when the platform motion is accurately known. And the second row shows the corresponding results when the platform motion has some uncertainty. The robot's walking is stable in both cases. The inherent robustness of controller can handle some of the platform motion uncertainty, although the robot motion is a bit shaky as compared with the first case. The tracking performance of the controller for nominal and uncertain cases are shown here. Overall, the simulation and experiment shows good trajectory tracking performance. The base pitch for uncertainty case shows a relatively large variation in PyBullet and experimental results as compared to the nominal case. This highlights the fact that real-world application or realistic simulation will be affected by uncertainties. A better estimate is a must for robust performance. The torque profiles closely matched for the MATLAB and PyBullet simulation and experiments. The torque saturation was implemented in MATLAB to ensure the simulated model closely resembles the hardware. This, along with the properly tuned PD gains, resulted in a better torque profile comparison for MATLAB, PyBullet, and experiment. In conclusion, in this work, the robot platform system is modeled as a hybrid time-varying system consisting of continuous phases and state-triggered jumps. A continuous control law was derived to provably stabilize the system during each continuous phase. Lyapunov-based stability analysis was performed to derive conditions for provably stabilizing the overall hybrid time-varying control system. Simulations and experiments were performed to validate the proposed strategy. In our ongoing and future research, we would explore real-time state estimation for a dynamic platform with unknown movements. This appears to be a reasonable way to handle dynamic platform with unknown motions or dynamics. We would also explore online motion planning of legged robots on dynamic platforms and robust control of hybrid time-varying system with state-triggered jumps. We feel that these are the immediate tools required to get a robust dynamic walking on dynamic rigid platforms in unknown complex real-world environments. The references we used for this presentation are listed here. Here is the picture of some of our lab's past activities. Reach out to us for any questions. Thank you.